Alright, so here's a fairly straightforward extension of one of the theorems of the book. One of the directions is actually given in the book, so I'm literally going to copy it down. I'm going to put in quotations so that I'm not plagiarizing. And so, as in the text, I'm also repeating it instead of having you look it up, just because it's good for me to go over this again and kind of say it out loud and work through it. So anyways, suppose R is a division ring and I a non-zero, and I guess this is a quote, so I is a non-zero ideal in R. If A is non-zero is in I, then so is the element 1, which is A times A inverse. It is clear that the only ideal of a ring containing 1 is R, because you just take 1 and rings are closed if you multiply it by anything in the ring, so you just multiply 1 by anything and you get the thing, so it's the whole thing. Hence, I is equal to R, and then he says some other stuff, but anyways, this proves that the only ideals in a division ring are 0 and R. So now suppose the other direction, 0 and R are the only ideals in R. If A is a non-zero element which is in R, then I, which we will have the collection of all elements R times A, where R is in R, is a non-zero, non-zero because it contains R, left ideal. So I equals R. I have to scroll down. So 1 is in I, so there exists some element R in R such that Ra equals 1. So let's see here. So RA equals 1. We want AR to be 1 as well, so that we confirm that R is the inverse of A. So now, what do? We take RA, and this is just a trick. RAR is obviously, we do associativity here. This is just R, so RAR is 1, is R, so R minus RAR equals 0, so R times 1 minus AR equals 0, and so R is non-zero, and this multiplication is 0, and because this is a division ring, you know that this implies that 1 minus AR must be 0, or AR equals 1. Thus, A inverse is R, which is contained in R. See here. So, oh wait, no. Did I say this is because this is a division ring? No, that's backwards. That's backwards. Why do we know this? A ring is a division ring if and only if 0 and R are the only left and right ideals. Oh. What about zero divisors? Is that a problem here? Okay, so I just looked it up online, and I hope I remember to remove it from this video. But there is something that we need to do here. We need to this last claim follows from the fact that if AB equals 0 and A and B are non-zero, wow, that is an FACT, and A and B are not 0, then since RA is equal to R, and why is this? This is because RA is an ideal, or no. We know that the ideal generated by left, R times A is an ideal, and it contains A, so it's not 0. Is this a left ideal or a right ideal? It's one of the two. But whatever it is, it has to equal R because it's not 0. And we also know RA equals 1. Then you take R, multiply by AB, and then what you get is this. So this is an element of big RA times B. But RA equals 1. Wait, hold on. Right. AB equals 0. So R times AB equals 0. But this is equal to RA times B. And RA is 1, so that's B, which is 0. Why did I have to use this thing here? I don't know if I did. Right. So let's see if we just started from here. R times this product AB. So AB equals 0. So suppose AB equals 0 and both A and B are non-zero. Then, see here. So let's write it like this. From the fact that if AB equals 0 and A is not equal 0, then since RA equals 1, R times AB, which is just RA times B, but that's just 1 times B, equals 0. Okay, and then... Okay, so cool. We're back on track. So 1 minus AR must be 0, or AR equals 0. So, thus, A inverse is precisely R, which is contained in big R. So, R contains such an inverse, A inverse, for all A is an R set minus 0. I think this might be R star. Yeah, let's call it that. R star. Maybe the star goes at the bottom. I forget. I think it goes at the top. Hence, R is a division ring. So there we go. Now we've completed the proof.